invite to come here. And in the introduction, the thing that I like the best is he's talking about the signal processing family. I really like that. This is a talk that I give a few times in these trips I make these days. And the way I have designed the talk is probably not the best way for this particular audience, in the following sense. Oftentimes, I go into an environment where there would be nobody working on nonlinear signal processing. And so I spend a lot of time motivating the work. Why should you do signal processing? And then spend about 20 minutes doing that, and then take the rest of the time introducing a couple of concepts. The second thing that I do is, or second goal that I have, is to really talk about not being afraid of nonlinear systems. Okay. In the sense that people are worried about the complexity of conceptual complexity. People are worried about the implementational complexity. All right. So the talk is designed to actually show a couple of situations where conceptually and implementationally it's very, very simple. So in some sense, I'm trying to humanize, in some sense, at least less demonize, or whatever has been demonized, I'm trying to actually take it down to a level. So let me start with a quote from Wilson Drew, very old quote in the sense that he wrote a book on nonlinear signal processing in 1981, and this is from the preface. Okay, let me just read it here. He said, when confronted with a nonlinear systems engineering problem, the first approach usually is to linearize. In other words, completely ignore the nature of the problem. It is indeed a happy circumstance, he wrote, when solutions can be obtained this way. When it cannot, the tendency is to try to avoid the situation altogether, presumably in the hope that the problem will go away. Those engineers who forge ahead are often viewed as foolish or worse. Nonlinear systems engineering is regarded not just as a difficult and confusing endeavor, it is widely viewed as dangerous to those who think about it for too long. Now, I know that you don't belong to that group because I know that there are many projects in nonlinear signal processing that you do very well. So that's why I said in the beginning that perhaps the audience, the way I prepared the talk may not be the right one for this group, but we will see. So, as I said earlier, the first 15 to 20 minutes I'm going to actually spend looking at different applications where nonlinear signal processing help quite a bit. So the first application I want to talk about is in professional audio systems. Now, all of us probably have one or two audio components at home or at work, right? So you go to a store, you want to buy an amplifier or you want to buy a loudspeaker, you look at, oh, what's the spec? Total harmonic distortion. If it says 0.002 or something like that, you say, this is good. It reproduces the music faithfully, more or less. I should be happy with it. Now, these plots are total harmonic distortion measured for some professional audio systems. Again, provided by a JBL professional employee, Dr. Alex Voishviller. What happens there is the speakers are blaring at extremely loud levels, okay? And the nonlinearity of the loudspeakers are very, very high. Okay? Look at this thing, 150 dB SPL, you are getting close to 20% harmonic distortion. Okay? What that means is that when you go to a concert, You are certainly enjoying the ambience, and you are going there for the ambience, not for the music, because what you hear is probably very distorted from what it's supposed to be. All right. So what you can do is do one of two things. One, you can build very expensive loudspeakers that are precise, and that they will tend to be very, very expensive. Or you can do what the smart people would do, use signal processing, design a pre-equalizer, distort the music or audio sufficiently such that when in cascade with the loudspeaker, what you get here is what you started out before the pre-equalization process. Okay. Now, I usually play some clips to demonstrate how well these things can be done. Unfortunately, my experience typically is that when I do that, I play the music through highly distorted audio systems, and you cannot hear the difference. Okay? But if you actually, if you are in an environment where your speakers are linear, you will hear the difference. So instead of playing the music, what I'm going to do is I'm going to just show you the spectrum of the signals involved so that I can explain to you what happens. Okay? First of all, there are 3 plots in there, even though you can only see 2. Okay? It's because I do such a good job of pre-equalization. Okay? So what it is this signal. This is the original signal, the red. Okay? And the blue is supposed to be, it's really on top of that. Or the red is on top of the blue. All right? The red is equalizer combined with the loudspeaker output. Okay? And this magenta colored plot is the loudspeaker output signal with no equalization. And this whole work was done on a woofer type system. So I only plotted frequencies from 0 to 1000 hertz. Okay. So what you see here is there is 10 to 15 dB difference at the low frequencies. Okay. And drum sequences and things like that, you can distinctly hear the difference. Okay. Drums will become softer, which you may not want to be. Okay. Things like that. So I'm going to move on. I'm not going to play. I could have played the music, but I won't. Let me go into an example in image processing. This is an old example done about 15 years ago by one of my students. So the problem there is at that time, this was 15 years ago, we were trying to do a optical character recognition system for male images. At that time, and I haven't worked on this problem since then, so I don't know what the current technology for optical character recognition systems are. At that time, what people used to do was they would create a black and white image first, a binary image first, all right, and then apply the OCR algorithm and see what you get. So what we did is we did what was supposed to be the optimal fixed threshold to do this binarization. Okay. And got this. It's ugly, it's terrible, right? Because all the letters touch each other, there is nothing you can see there. And then we sent it through an OCR system. 15 years ago, technology was not that good, I agree. 6 out of 94 letters were recognized. Terrible. So what do we do? Well, one thought was to, first of all, do some pre-processing of this image. Okay. Maybe you can sharpen the edges, maybe eliminate some of the noise if you can. All right. Maybe things would be a little bit more distinct. Now, if you want to sharpen the edges, and if you want to use a linear filter, what do? You need a high-pass filter, right? Or something like a high-pass filter. High-frequency components need to be enhanced. But if you use a high-pass linear filter, what happens is you would also enhance broadband noise that might be present in there. So that's not a good solution for this kind of application. And if you actually look in the literature, you will find hundreds and hundreds of papers talking about nonlinear processing for this. Okay, so yeah, so Gianni Ramponi in the University of Trieste in Italy, he actually designed a nonlinear filter to do this thing. Now, this nonlinear filter was not that complicated. I think it had about three multiplications per sample or something like that. So many times when you talk about nonlinear filters, we think about very complex filters. Nothing like that. 2 or 3 or 4, maybe 5 multiplications. That's it. Okay, per pixel. Well, clearly the results are much better than before. Still not that great. Character recognition, not bad. 6 went up to 38. Okay. Then I had a student who actually looked at this problem, and he said, you know, Dr. Matthews, I don't think that the statistics here, the characteristics of the image here is the same as the image here. So applying a fixed processor to this image is not a good idea. You should use an adaptive filter. Okay. Of course, I like adaptive filters. I work on adaptive filters. And I said, go ahead, do an adaptive nonlinear filter. He designed an adaptive nonlinear filter, and that's what he got. Okay. So much, much better. And character recognition performance was also not too bad. Okay. Now, this was 15 years ago, and at that time, that kind of performance was actually pretty decent. Okay. So the point I'm trying to make here is you can do a decent job at least, which you couldn't do with fixed filters or which you couldn't do with linear filters, using linear, nonlinear, and adaptive processing in this case. Okay. And again, the complexity was about less than 5 samples per multipliers per pixel. So fairly straightforward implementations. This is a communications group, so I must have at least one application in communications, right? So I will give you 2, just for you. So this was a project that we worked on 2 or 3 years ago. And the problem here was that you had an X-band communication system where the antenna was being used for transmitting and receiving, but over 2 separate channels. Okay. And the nonlinearities in the antenna caused the transmit signals to leak into the receive signals, and the receive signals perhaps to go into the transmit signal. And our problem was to actually take care of the receiver, the problems at this end. Okay. So we looked at this problem and said, hey, it looks almost like an echo canceller. Okay. And we basically designed a nonlinear echo canceller for this particular problem. And here are the results. Again, bit error occurs. This is without compensation, equalization, echo cancellation. Here is what you get with cancellation of the distortion. So again, nonlinear. This is adaptive nonlinear echo type cancellation for this particular problem. Does well. Let me actually bring up one other thing. One of the things that people don't always recognize, and it's really true, but communications people probably do recognize that too, is as you increase the order of modulation, for example, in QAM systems, even small amount of nonlinearities will make a big difference. Okay. So what I'm doing here is that I have a communication system, QAM system, and this axis is the number of symbols per, or number of bits per symbol. Okay, so you're going from 4 levels to 4,096 levels out there. Okay, and what you see, and I just introduced a small amount of nonlinearity into the channel. Didn't introduce any noise, so the only source of distortion is this small amount of nonlinearity. And what you find is, for lower orders, it doesn't make that big a difference. The same nonlinearity, but as you increase the model order, your errors go up to close to 90%. All right. So in these kind of environments, and I think these kind of environments are going to be more and more common as we move forward, there is nothing you can do if you do not take care of problems with nonlinearity also. Let me give you one other example, and this is in brain-machine interfaces. And one of the problems that we work on involves neural prosthesis. And part of the problem involves understanding what the human intent is by looking at signals collected from the brain. And we are using something called ECOG signal, electrocorticography signals. Okay? And what you do is you implant an array of electrodes in the brain just below the cranium. Okay? So it's not very penetrative. It requires a surgery, but it's not totally penetrative arrays. Okay? And then, in this particular case, what we're trying to do was we basically asked the patient to move his hands in different directions and recorded the positions of the hand, along with signals collected from the brain. Okay? And the question then we asked is whether we could estimate the location of the hand from the brain signals. Now, brain, human body, human brain, you don't expect it to be linear, do you? Probably not. But if you actually look in the literature, almost everything you find will actually talk about building a linear Kalman filter to track these movements. Okay? And if you do that, this is what you will see. The red is the actual hand movement. The blue is the estimated hand movement. The mean square error turned out to be about 7 plus 7.2 or 7.3 centimeters squared in this particular example case. And this was actually trained, the system was trained on one particular data set and then tested on another one. This is the test results that you're seeing. Okay? And you will probably say that it's okay, but not that great. Okay? And then I had a student who came to me and said, Dr. Matthews, why don't I try some nonlinear modeling here? Okay? And I said, fine, I like nonlinear models. So he actually got this result. The mean square error was about 4 point something, so it was about 50% better than the one before. And I'm going to guess that when you see this, you will say this is much, much better than before, right? Maybe? Okay. So, if you want to actually learn about nonlinear filters, I can suggest a lot of books. I used to only put my book in there, and then I decided maybe that's not the right thing. So now I put lots of books there. Okay. Now, let me ask you this question, and you should know the answer to this question. What is a nonlinear system? You're all motivated to do nonlinear filtering work now, signal processing work, but what is a nonlinear system? Any ideas? Any answers? Boy, that's a tough question, huh? Well, I asked the question because if you actually think about the definition, it says any system that is not linear is nonlinear. Right? Pardon me? Non-uniform behavior. It can mean anything, right? That can mean anything. It's a little too broad for my liking. Okay? But anything that's not linear is nonlinear. What it means is that you don't have a unified theory that you're actually going to come up with dealing with every possible nonlinear system out there, right? So you will find many different people working on different types of nonlinear systems. Okay. One of the systems that I have spent a lot of time working on is polynomial systems. I'm not going to spend a lot of time on this thing, and a lot of the applications I talk about, a lot of the ideas I talk about later do not necessarily need polynomial models, okay, or do not only depend on polynomial models, but I just thought that I would bring this up, introduce a couple of concepts, and then move on. Okay. So a polynomial system is one where the output y is a sum of polynomials in the input and the output samples. Simple. It can have feedback because you have the output sample. Okay. So here is a pth order polynomial. I is the order of this particular polynomial. Okay. So that seems reasonable, and people like these models a lot because many times you can think in terms of this being the next level. In the sense you have linear systems. This is one level higher, so it's an extension of some sort. Okay. It turns out that many concepts in linear system theory can be extended to polynomial system theory. For example, one of the things that's great about this system is that this system is linear in the parameters, in the sense that if you actually look at the output, it's the parameter multiplied by some nonlinear function of the input samples and the output samples, but then you just add them up. So that's the linearity I'm talking about. So a lot of the linear system estimation theory ideas can be applied to this particular problem. It turns out that even ideas that relate to frequency domain representation of systems can be applied in this situation with some extrapolation. Okay? So that's a good thing. So let me just give you a couple of different polynomial systems that people work on a lot. Truncated Volterra systems. People spend a lot of time working on those things. There is no feedback. Your output is just a linear combination of product of input samples. Okay. Or if you want feedback, a common model that people work on is bilinear systems. This part looks like linear, but nonlinearity comes through this product term that involves both the input and the output. So that's by way of introduction, and I did okay. So we'll be fine. So now I want to actually, if we have time, we will deal with two things. If we don't have time, we will only deal with one thing. Okay. The first thing I want to talk about is inversion or equalization of nonlinear systems. Again, what I'm going to do is I'm going to take one example in inversion of nonlinear systems and show that there is a fairly simple idea that you can use to invert these systems. Okay? And I will show you that that's a fairly general situation too. Before I do that, I want to say one more thing. Unlike linear time invariant systems, when you talk about inverses of nonlinear systems, you have to talk about pre and post inverse separately because they may be different. For linear time invariant systems, you create the inverse, you put it before, you put it after, it's still the inverse. That's not necessarily the case for nonlinear systems. So you have to be careful. Okay? But the good thing is, every system that I am going to talk about, it turns out that the pre and the post inverse are the same. Okay? Just so happens. All right. So now, I'm going to actually work with a very, very specific model. Okay? So I have the math here, and I have a block diagram here. So let me start with the math. Essentially what it says is, my output of the system Y depends on three different nonlinearities. One is a nonlinearity G. The only constraint I place on G is that it's invertible, and that is memoryless. Okay. Then I have a nonlinearity H that involves both X and Y, output and the input. The only constraint I have here is that X of n is not here. If you put X of n there, you can still come up with a solution, but you don't have an explicit solution like I'm going to derive next. Okay? You will have to do iterative search for the solution. Okay? And again, similarly, F has the same kind of properties as H. Okay? So I'm not specifying anything about the nonlinearities other than these light constraints. Okay? So from that perspective, it looks like a very, very general model. Okay? Now, I have this block diagram, and it makes it look very, very simple. Right? What do? You have a nonlinearity, you have another nonlinearity, you multiply them together. To the output of that product term, product operation, you add the output of another nonlinearity. Okay? And it looks fairly simple too. Okay? Now, I'm going to take this simple structure, representation, and I'm going to show in 1 minute that you can actually create its inverse. Okay? And it turns out that its inverse, that inverse is both the post-inverse and the pre-inverse. But I'm not going to prove that to you, but I will tell you how to get there. Okay? So, I want to invert this system. So, from Y, I want X. Right? Let's just work on it. If you take Y and subtract this signal, you get that signal, right? Then if you divide that signal by this signal, you get G. The output of G, right? G is invertible. So invert that, you get X. So here it is. Here is a system. Okay? So simple, so straightforward. Okay. So the only thing that I have done differently here is I recognize that wherever Y was in the other picture, that's the input of my inverse system. This is the post-inverse I have done here. Okay? And I replace that Y by U as the input to the system. And wherever X came in the previous picture, that was going to be the output of this equalizer or inverse system. Okay? And I replaced that X by Z. That's the only difference I have done. Okay? Now, so you get this. That's your inverse structure. Now, if you want to show that this is also the pre-inverse, what do you have to do? Just find the post-inverse for this and show that that is the same system that you started with. Okay. Same ideas you can employ. Okay. So the reason why I actually do this thing is, many times when people talk about equalizing or inverting nonlinear systems, people actually start wondering how we can do this thing. Okay. But there are creative ways in which we can come up with very, very simple and straightforward ways of dealing with the problem. Okay. Now, I don't know if this system is stable or not. We won't deal with it because we have to know a lot more about the forward system before I can say whether this system is stable or not. So this is a very general statement about how you can go about solving the problem that I'm doing. But now the question is this useful for systems that you might be interested in? Let me just give you an example. Let me take a very simple or very common example, that of the bilinear system. Let me show you how you can invert a bilinear system using the previous theory. Okay? So if I write the bilinear system a little differently like this, what I'm doing is I'm taking x of n and every term involving x of n from here. Okay? And write like that. So this is my G. It turns out it's an identity system, and I'm not going to complain if it's an identity system. I know what the inverse of that system is. And this is your H, I think. The system that multiplied the G, nonlinear. I think it was F, right? Or H, one of those. Right? And that turned out to be linear too. Again, I'm not going to complain. And everything else that's left there, I'm going to call it the nonlinear system that added up to the product term. Okay? Suddenly, you have a representation that is in the exact form as what we started with. And there it is. That's the inverse of a bilinear system. Okay? Now, this is not a polynomial system, okay, because this is a polynomial divided by a polynomial system. There is a special name for that. We call it a rational system. Okay? But so the inverse of a polynomial system is not necessarily a polynomial system. So what? I'm not going to complain, right? If I can implement it and if I can implement it in a stable manner, I will be happy. Okay. Again, whether it's stable or not, I'm not going to deal with it right now. There are ways in which you can check if it's stable, okay? But we won't worry about that for the time. So there is one other thing I want to actually talk about. I talked a lot about not knowing whether it's stable or not, whether the inverses are stable or not, right? So many people have dealt with the same problem, and long time ago, in 76 or so, 1976 that is, Shetson actually came up with the theory of pth order inverses. Okay. What it is this is the post-inverse and the pre-inverse. You have to deal with them separately. Let me just work with the post-inverse. Tp is said to be the pth order post-inverse of this nonlinear system H if the cascade of the two together gives you the input signal plus a residual, and that residual will have a nonlinear expansion, okay, that involves only p plus 1th order nonlinearity and higher. Okay. And the same kind of thing for pre-inverse. And I told you about Shetson. Then what Shetson did is he realized that the pth order inverses are not necessarily unique. Okay. And he said, if I put some more constraints on the pth order inverses, I can make them unique. And he actually solved for the unique solution after putting those constraints in. And in the process, he got some very elegant solutions, but they were also fairly complicated because the structure turned out to be somewhat more complex. Okay. In the early 90s, a couple of Italian researchers took out some of those constraints and said that I can make my processor much simpler. Okay. And then a little later, one of my old students, Alberto Carini, and actually I should have put in Giovanni Sicuranza's name in there too. It's the three of us that wrote the paper at that time, and it's essentially Carini's work. He simplified it even more. Okay, so I will actually show you what he did. I will just show you the solution because the solution is really elegant. Okay, and I will show you the solution for a very specific nonlinear system. Again, even though it looks simple, you know that out here I'm talking about practically any nonlinearity out there. Okay, so I'm looking at a nonlinear system that is a linear system in parallel to some arbitrary nonlinear system. Okay. Now, I have two constraints that I'm going to impose upon this problem. And the constraints are A is invertible, the linear system is invertible, and that N, the forward nonlinearity, is a stable system. Okay. Physical systems, probably that's a reasonable assumption to make. Here is the ideal equalizer. Again, if you actually proceed like we did earlier, this is a straightforward derivation. Okay. Once again, we don't know if it's stable or not, so we will start talking about a pth order inverse. Okay. It turns out that the first order inverse is nothing but the inverse of the linear system in there. Now, if you want the second order inverse, what you do is add in cascade to that a block like this. If you want a third order system, add the same block in cascade to the output there. Fourth order, same thing. The point I'm trying to make is the pth order inverses can be made in a systolic manner. Oops. Sorry. Oh, that's not good. In a systolic manner, right? It's the same block repeated whether you're doing software or hardware. All you have to do is build this block. Okay. Now, is it stable? Well, let's look at it. A is known to be stable, so A inverse, I'm assuming it's stable, right? N, we said, is stable. So this part is going to be stable. This is an identity part, so that part is going to be stable. So things are going to be stable here, right? Repeat the same thing. Okay. So based on our assumptions about the stability of the forward system, the inverse, pth order inverse, also turns out to be stable. Okay. So what we're hoping is that as the order increases, we will actually get closer and closer to the ideal inverse. Okay. But whatever order you choose, the results turns out to be a stable system. Okay. Now, this is a quick example. This was a loudspeaker nonlinearization problem. We tried up to fifth order equalization, and basically the second order harmonic distortion went from this large peak to something smaller and smaller and smaller. Just showing an example that these kind of things do work. Okay. So I have 5 minutes to 11. I can do one of two things. I can go on. Okay. Oh, great. I will not take that long. I don't think so, at least. In that case, let me actually talk about one adaptive filter. Okay. So what I'm going to do here is something a little different from what you might have been expecting. I'm going to talk about adaptive filters used for system identification only. And whatever I'm going to do can be applied only for that application. That's it, in that situation. Okay. The good thing is, I'm going to actually tell you about an adaptive filter that requires only one multiplication per time instant, regardless of the complexity of the system model. The system model can have 100,000 coefficients. I will still only need one multiplication. Okay? So the key here is, again, you're doing system identification. What that means is that you have complete access to your input signal. In fact, not only that you have access, you can design your input signal. Okay? Everybody here knows about adaptive filters, I'm sure. You have a desired response signal, you have your input signal, you want an adaptive filter that the output of which you want to make as close to D of n as possible, right? And your goal is to minimize some convex function of the estimation error. So the system model. This is important. The system model can be any nonlinear function as long as it is linear in the parameters. Okay. So the output y would be a coefficient vector times an input vector, where the elements of the input vector are any nonlinearity you care about. It doesn't matter to me. Okay? As long as there are no coefficients built in there. Okay. So if you do that, and let's assume that there are n coefficients in H. Okay? Now I'm going to design an input signal that's periodic. It's not a tone. I'm going to just get a broader band periodic signal, an n-periodic signal. And the key thing here is, and what makes things work, is if x is periodic, so is y, assuming that it's a time invariant system. We are going to assume that we have a time invariant system that we are trying to identify. Okay. Later on, we are using an adaptive filter. We will say, okay, we will let it slowly vary. Okay. And but don't worry too much about that part right now. So if x is periodic, y is, so is this input vector that's a nonlinear function of x. Right? Okay. Now I'm going to walk you through the derivation, okay, because it's fairly simple. So now this x1, x2 up to xn are the n different values my input vector can take. It's periodic, so I can only take n different values. Okay. Now, put all of those vectors together, form a matrix C. Okay. Now, I'm going to assume that Z is invertible. Now, can I assume that? Of course. I have complete control over the selection of my input signal. So I can make sure that I design an input signal in such a way that this is an invertible matrix. Okay? So that's not an assumption. It's something that we as engineers can do. All right? So let W be that inverse of the Z matrix. Now, so now I want a new vector C such that it is W transpose times C. Such that the coefficient vector H is W transpose times C. Now you might ask me, is that reasonable to assume? Well, you know W is invertible, so W transpose is invertible, right? And W transpose and C is going to be inverse of W transpose times H. So clearly it's doable, right? Not a problem. So if that's the case, then your Y of n, if I replace H transpose by W transpose C, H by W transpose C, it becomes C transpose times W times XF. Just substituting that here, right? Now, here is the thing you have to remember. Remember, W is the inverse of Z, right? Z comprises of every vector value that X of F can take, right? So W times XF, X1 or X2 or up to Xn, any of them, is going to be either 1 or 0, right? Because W times Z is identity, right? So what that means is that this quantity is 1 or 0, and the product is going to be just one element of C, right? Okay. So I just wrote all those things, and so you end up this thing, and so you get output Y is equal to one element of C. And so that's new parameter. By the way, C is an equivalent parameter for H, right? Because if you know C, you can get H. Correct? But Y, every time Y takes one value of C. All right? So, what do you want to do? You change the adaptive filtering problem, estimation problem, into one of estimating C rather than H. So here is my problem now. Let's design an LMS adaptive filter. Minimize or reduce the squared error between D and Y, but you know Y is one of the C's. All right. And you want to update the C values. Right. What do? Differentiate with respect to each of the CKs maybe. That's the gradient. Subtract a constant times the gradient. You get your adaptive update, right, for the LMS. So, of the n, capital N different values of C, only one of them appears at time small n. So the gradient is going to be 0 every time except one, for every coefficient except one coefficient, right? So what happens is that you update Ci, if I is equal to n mod, that should be n, not m, n mod capital N, okay? Otherwise, you just keep it like that. Next time, you'll update the next value of C. And the next time, you'll update the third value of C, and so on and so forth, okay? So look at this thing. You may have 100,000 coefficients. You only need one multiplication. You will iteratively, slowly, and steadily get there. Now, does this slow down convergence? No. We have actually shown that the convergence speed is comparable to the normalized LMS adaptive filters. Okay. This is just an example showing that it does converge for, this was a truncated Volterra model. This is some other model, Flan model, that contains cosines and sines and things like that. Okay. It works beautifully in this application, but you can only apply it in the system identification problem where you can design your input signal. Okay, that's the only constraint. And that can be a big constraint in many applications. But why did I bring it up? Or why did I actually bring this particular problem to you? Again, I want to show that you can implement nonlinear adaptive filters in a very efficient manner, at least in some circumstances. Just like I showed earlier, that you could invert or equalize for many nonlinear systems in very efficient ways. Okay. So that brings me to the conclusions. So I overviewed some basics of nonlinear systems with the goal of demonizing some of the worries that many people may have. The point I tried to make earlier is that significant advances in many practical applications are possible through the use of nonlinear signal processing that we saw, but in many cases, significant advances are possible only through the use of nonlinear signal processing. Okay. Now, there may be situations where computational complexity is an issue, but that shouldn't stop you from working on that. Again, think about how quickly computational power has increased. Okay? Things I couldn't do 5 years ago in real time, I can do now. If you come across a problem that you cannot do in real time now, still work on it, because you will be able to do that 5 years from now or 3 years from now. Okay? And with that, I will show you a list of many of my collaborators and a lot of my students. Giovanni Sicranza, Dehiyun, he's in Seoul, Korea. Sicranza and Ramponi are in Trieste, Italy. Nicola Psidis is in Athens. Alberto Carini is in Urbino. Honky Beck is in Chonbuk National University in Korea. This group used to be either my students or visiting scholars in my lab. Jiangshi Li, Thomas Panikkar, Shan Mo, Mustaq Said, Theron Jameson, Shreyas Panel, and there are a couple of people who didn't want to give me their pictures, so I will not put them there. So they were all my students sometime or other, and most of the work were done by these folks. All right, and I spent a lot of time talking about the work that Alberto Carini did. All right. That's it. Any questions? I think I did okay. I didn't take quite 1 hour. Yeah. I think so. Yeah.
This is not my field. My field is very simple. Sure. So when we're talking about adaptive nonlinear filters, usually the idea is to try to assume a model that the coefficients are linear. So the adaptive part is based on a linear relation for it, or
Okay.
there is also...
It doesn't have to be. Even though a lot of the things I have done does assume linear in the parameters models. Okay? But it doesn't have to be. You can, gradient algorithms are applicable to both cases. Sometimes the problem would be that the error surface may turn out to be multimodal. Okay, so you may actually get into local minimum and things like that. That's the only issue that might be a problem. Okay. Anything else?
Most of the people are missing communications going out from the nonlinear is because the change in the distribution of the noise is not just a problem, because that's the problem with removing nonlinear interface. Connected with this is, let's say, some contradiction that without the Gaussian assumption alone, still people minimize the quadratic curve. I don't know, for example, like, I think I did much practicing in this practicing. Of course, procedures are not linear, and MMC is not quite useful for determining optimality of the process. Could you comment on that?
mean square is not
The mean
optimal.
square error is
Yeah.
linked with Gaussian.
Right.
People in nonlinear practice in the survey.
Exactly.
I don't think it's serious, but from the point of view of
Right.
formalities, and
Right.
all that,
You can derive cost functions that are not squared error based. In fact, there are people who do a lot of variations of that, and even convex combinations of
yeah.
multiple cost functions. I have spent a little time looking at L1 based algorithms.
Now it's the question.
You know what? I did it before I knew anything about sparse, though. I stopped working on that in the 80s, actually, but maybe I should go back.
It's a talking word.
Right, yeah. And higher order cost functions, fourth order and third order and things like that. Then, of course, depending on the application, there are also people who work on totally different cost functions derived based on more, within quote, information theoretic criteria, especially in the context of independent component analysis and all those kind of things. So, and where Gaussianity is strongly discouraged, right? So, yeah, I know things will work for the kind of applications that I talked about, or just basic estimation problems, or for the supervised estimation problems. Mean square works.
Yeah, that's why I said it's more
Right.
formal than practical.
Right.
Complain about it.
Yeah, right. Yeah.
Yeah,
The system identification solution that you presented, which you mentioned that it's only valid for the case where you can design the input. How often do you,
I would like to design the input because then I can control the convergence behavior and things like that. But the only constraint really is that the input is periodic. That's okay. Go on.
so how often do you encounter this in practice versus the case where you cannot have this periodicity property? And can you give some examples of either case?
Well, I had the same question a couple of talks ago. And the example I actually gave at that time was in communications. If you're actually dealing with a pilot signal, you have complete control over the pilot, right? So that's one example where you can actually easily show that it's useful. And there are also situations where you use pilots, dedicated pilot channels and things like that, right? So you can keep doing this thing, and this is next situation where you just have a simpler.
And which would be a situation in which you cannot design this?
Oh,
Usually in communications you can.
no.
The problem will be only the size of the channel of the matrix theta.
Say it again.
The size
Uh-huh.
of the matrix theta is going to change depending on the application.
Right. Yeah.
It's like whenever you have using a table, like in such a way you can quantize.
Right. Yeah, again, the size of the channel itself, mathematically or conceptually, you can have a large N and be done, right? You can deal with channels that way, but it's probably not the best to do. Simple example, just take an audio processing example. Okay. So yeah.
But will you be able to design an input that's similar to the actual?
Again, yes and no. If you are dealing with, let's say that you want to measure the room acoustics, okay, and let's say that the way you are measuring the room acoustics is by creating an artificial signal and actually sending it out, collecting it back, you can do that precisely. Absolutely no problems. Okay. However, if you also want to actually track the changes, suddenly you have to use the signal that you have. Right? Then you cannot.